Welcome back to Statistics. Before we start today's lecture, let's review the last lecture. We started the last lecture by talking about the positive z equal line and the negative z equal line. The positive z equal line is a diagonal line on a scatter plot that passes through the point of averages. The standardized coordinates of each point on the line fits this equation. The z of y is equal to the z of x. The negative z equal line is also a diagonal line on a scatter plot that passes through the point of averages. The standardized coordinates of each point on the line fit this equation. The z of y is equal to the z of x times negative 1. We spent most of the last lecture by talking about the correlation coefficient, which is known as R or Pearson's R. The correlation coefficient tells us how strong is the relationship between two continuous variables. Correlations always lie between negative 1 and 1. There is no such thing as a correlation of 2 or 3 or 500. Correlations can be positive or negative. Positive correlations always lie between 0 and 1. If two variables are positively correlated, we can plot them on a scatter plot and draw a line that shows the general trend in their relationship. The line goes up from left to right. That is, it has a positive slope. The line shows the trend is the positive z equal line. When the correlation is 0, there is no relationship between x and y, and the dots in the scatter plot are not close to the line. But as the correlation increases, the relationship between x and y gets stronger, and the dots get closer and closer to the line. Here is a correlation of 0.5. You can see the relationship is stronger and the dots are getting closer to the line. Here is a correlation of 0.8, a correlation of 0.95, and here is a correlation of positive 1. When r is equal to 1, x and y have a perfect positive relationship. You cannot get a stronger positive relationship than this. Negative correlations always lie between negative 1 and 0. If two variables are negatively correlated and we plot them on a scatter plot, the line that shows the general trend in their relationship goes down from left to right. That is, it has a negative slope. This line is the negative z equal line. Here is a correlation of 0 again. X and y are unrelated. Here is a correlation of negative 0.5. You can see the relationship is stronger and the dots are getting closer to the line. Here is a correlation of negative 0.8, a correlation of negative 0.95, and here is a correlation of negative 1. When r is equal to negative 1, x and y have a perfect negative relationship. You cannot get a stronger negative relationship than this. So when r is equal to positive 1, there is a perfect positive relationship between x and y. Okay, so when r is equal to negative 1, there is a perfect negative relationship between x and y. And when r is equal to 0, there is no relationship between x and y. In the last lecture, we also discussed the strengths of the correlations. The strength of a correlation has nothing to do with whether it's positive or negative. Instead, the strength of a correlation depends on how close the correlation is to positive 1 or negative 1. For example, a correlation of positive 0.8 and a correlation of negative 0.8 are equally strong. They both indicate a very strong relationship between x and y. Similarly, a correlation of positive zero point 0.5 and a correlation of negative zero point 0.5 are equally strong. They both indicate a strong relationship between x and y, although not as strong as a correlation of zero point 0.8 or negative zero point 0.8. This table summarizes the strengths of many correlation coefficients. We also showed another way of thinking about x and y when they are correlated. When two variables have a negative correlation, people high on x tend to be high on y. And people low on x tend to be low on y. But when two variables have a negative correlation, people high on x tend to be low on y. And people low on x tend to be high on y. At the end of last lecture, we talked about how to calculate R. We say that R is the mean cross product of z-scores, and that you should memorize this definition because this is so useful. To calculate R, we first need to calculate the z-scores of x and y. Second, we calculate the cross products of the z-scores. That is, for each person, we multiply together the z of x times the z of y. Third and finally, we calculate the mean of these cross products. This mean is R. That is, R is the mean cross product of the z-scores. So now we are ready to go on today's new material. So now we are getting the class exercise. And be sure you have a handout with you. There are two tables on the handout. We will start with table 1. And before we start, there are two purposes for this exercise. The first purpose is to fill in the table and get practice calculating the correlation coefficient. But the second is to get the real feeling for the correlation coefficient and its underlying logic. Before we get started, I want to remind you that R is the mean cross product of the z-scores. There are 3 steps to calculate the correlation coefficient. The first step is transform x and y into z-scores. The second step is to cross multiply the z-scores to get their cross product. The third step is to find the mean of these cross products. This mean is R because R is the mean cross product of these scores. Okay, so this slide shows the table filled in correctly. So now, which number on the table represent the correlation coefficient? Okay, the correlation is equal to the mean of the cross products, so the correlation is 0.750. Now, if you didn't get that value as a correlation, something went wrong. And now is the time to find out what went wrong. So make sure you get the value 0.750. Here is the scatter plot of the data you just have been working with. The correlation is 0.75. There are only a few individuals, but you can see the positive trend of the data from left to right. Now we are going to do the exercise with table 2. So this is the data we are going to be working with. Now I want to draw your attention to these numbers in the raw scores for x. These numbers have been closed out, but you can see what they are. So where have you seen these numbers before? These are the same values for x that are in the table 1. You were just working with these numbers. We will call these the old x values. Right next to them are some other values for x that we will call the new x values. Now I calculated these new x values by taking the old x values and doing something to them. So what I did is I got each new value of x by adding 3 to the corresponding old value of x. For example, I took the old value of 12 and added 3 to it, and I got the new value of 15. I took the old value of 14 and added 3 to it, and I got the new value of 17. I took the old value of 10 and added 3 to it, and I got the new value of 13. I did the same thing for all the other old values and got the entire new set of new values. What I did was a transformation. Earlier in the semester, we learned that transformations are taking one kind of score and turning it into another kind of score. For example, we learned how to transform raw scores into z-scores, z-scores into percentiles, and percentiles into raw scores. Today, for table 2, I took the old x scores and transformed them into the new x scores. Here is the formula I used the transformation. The old x score plus 3 is equal to the new x score. I also did a transformation on the old y values. These old y values are the same ones as you used minutes ago in table 1. I transformed these old y values into new y values. What did I do to the old y values to get the new y values? I transformed the old y scores into the new y scores using this formula. The old y score times 2 is equal to the new y score. In other words, I took the old y scores, multiplied them by 2, and got a new y scores. For example, I multiplied the old y score of 7 by 2 and got the new y score of 14. I multiplied the old y of 5 by 2 and got the new y of 10. I multiplied 3 by 2 and got 6, and so on. Now in this exercise, we are going to use the new x and y values. And what I want you to do is calculate the mean and the standard deviation for the new values. That means you will need to fill in all the cells of the table that I have highlighted here in the yellow. Here are the correct numbers. Let's take a look at the new x values with their mean and standard deviation. The mean of the new x values is 11. The standard deviation is 4. Remember that the new x values are equal to the old x values plus 3. So let's see how the transformation affected the mean and the standard deviation. We need to compare the new mean and standard deviation with the old mean and standard deviation. So let's write the mean and the standard deviation of the old x values down here. So what's the easiest way to find out the mean and standard deviation of the old x values? So we calculated the means and standard deviations for the old x values when we did the exercise for table 1. So take a look at the table 1 and fill that out. So the mean of the old x values is 8 and the standard deviation of the old x values is 4. So now let's compare these numbers with the new mean and standard deviation. The mean of the old x value is 8. The mean of the new x values is 11. So when we added 3 to the old x values, the mean of the new x values was also increased by 3. And this is a general principle when we do the transformations. If you add the same number to all values of the old variable, the mean of the new variable is increased by the same number. The same general principle applies to subtraction. If you subtract the same number from all the values of the old variable, the mean of the new variable is decreased by the same number. So next, let's see what happened to the standard deviation when you add 3 to all. The standard deviation for the old x value is 4. The standard deviation for the new x values is also 4. Okay, so even though we increased all the values of x by 3, the standard deviation didn't change a bit. Here's why. We increased all the x values by 3, but that caused the mean of the x values to change by 3 also. So the distance between x values and their mean didn't change. With the data, the values goes up and the means goes up at the same time. So the distance between the values and the mean stays the same. So this is another general principle about the transformations. If you add the same number to all the values of the old variable, the standard deviation of the new variable doesn't change. And since subtract is a form of addition, if you subtract the same number from all the values of the old variable, the standard deviation of the new variable doesn't change. So this is a summary. If we do a transformation that involves adding or subtracting a number from the values, the mean changes, but the standard deviation doesn't change. Now let's consider the new y values. The mean of new y values is 8 and the standard deviation is 4. We got the new y values by multiplying the old y values by 2. Let's see what happened to the mean and the standard deviation. For the comparison, we need the mean and standard deviation of the old y values. So what are the old mean and standard deviation? So the mean of the old y value is 4 and the standard deviation is 2. So let's compare the mean of the old y values, which is 4, with the mean of the new y values, which is 8. Now remember, we got the new values of y by multiplying the old values by 2. So what happened to the mean? Right? So when we multiply the old values by 2, the mean was also multiplied by 2. And this is the general principle of transformations. If you multiply all values of the old variables by the same number, the mean of the new variable is multiplied by the same number. If you divide all values of the old variable by the same number, the mean of the new variable is divided by the same number. Now let's look at the standard deviations. Here is the standard deviation of the old y values, which is 2. And here is the standard deviation of the new y values, which is 4. To get the new y values, we multiply the old y values by 2. So what happened to the standard deviation? When we multiply the old values by 2, we also multiply the standard deviation by 2. Remember, the standard deviation measures the typical distance of the values from their mean. When we multiply the variable by 2, we double the distance of each point from the mean. And this is a general principle with the transformations. If you multiply the old values of the old variable by the same number, the standard deviation of the new values is multiplied by the same number, and this is the same for deviation. If you divide all values of the old variable by the same number, the standard deviation of the new variables is divided by the same number. This is a summary. If we do a transformation that involves multiplying or dividing the values, the mean changes and the standard deviation also changes. So we've seen how transformations affect the mean and the standard deviation. Now let's see how they affect the z-scores and correlation. So go ahead and fill out the rest of the table. So here are the numbers. These are the z-scores and correlation we get when we use the new values of x and y. So let's compare the new z-scores and correlation with the old z-scores and correlation. We got exactly the same numbers when we use the old x and y values. Adding 3 to the old x scores didn't matter. Multiplying the old y scores by 2 didn't matter as well. So we got exactly the same z-scores, the same cross products, and the same correlation coefficient r. So if you transform the old variables by addition, subtraction, multiplication, or deviation, the z-scores and r stay exactly the same. But it turns out there is one exception. Dividing or multiplying the same number usually doesn't change the correlation, except there is a catch. Dividing or multiplying by a negative number reverses the sign of the correlation, either from the negative to positive or from positive to negative. So let me show you what I mean. Here are the x and y values we started with in the first exercise today. R is equal to 0.75. We call these values old x and y. So now we add a new x and y over here. The new x and y values are the same as the old x and y values except for one difference. The new y values are equal to the old new values multiplied by the negative 1. For example, the old y value is 7. When we multiply it by negative 1, the new y value is negative 7. The old y value of 5 is transformed into the new y value of negative 5. The old y value of 3 is transformed into the new y value of negative 3, and so on. Now, because we multiply the old y values by a negative number, that leaves the size of the correlation the same, but reverse the sign from the positive to negative. So on the left, we have a correlation of 0.75, and on the right, a correlation of the negative 0.75. I will show you the scatter plots of these two sets of numbers. First, I will show you the scatter plot for the old x and y values. You saw this graph earlier today. It shows that the x and y values are positively correlated and going from left to right. The line is the positive z equal line. Next, I will show you the scatter plot for the new y and x values. As you can see, multiplying the old y values by negative 1 has reversed the position points and the slope of the line. Now, the points follow the negative z equal line, but the strength of the correlation remains the same, which is 0.75. It's just a negative instead of positive. So the main thing to understand is this. Multiplying the values of an old variable by a negative number doesn't change the strength of a correlation, but multiplying a negative number reverses the sign of the correlation from positive to negative or from negative to positive. The last point we are going to cover today is this. The correlation is not the same as causation. Here is another way that the scientists express the same idea. Correlation does not imply causation. If we find a correlation between two variables, that doesn't mean one of the variables causes the other one. And here is another way of expressing this idea. If x and y are correlated, it is not necessarily true that the x causes y or y causes x. It is very important to remember that the correlation and causation are different. Sometimes a correlation between two variables indicates that one is the cause of the other, but sometimes the two may be correlated even though there is no causal relationship. Scientists call it a spurious correlation when x and y are correlated but neither x nor y is the cause of the other. So to repeat it, a spurious correlation is a correlation that does not involve with causation. Here is a website called the Spurious Correlations. The spurious correlations are the real correlations based on the real data. This graph is from the website. It shows that the cheese consumption in the US from the year 2000 to the year 2009 and also the number of people who died by becoming tangled in their bed sheets during the same period of time. On the x-axis, there are the years 2000, 2001, 2002 up to 2009. The red line shows the cheese consumption during each year. In the year 2000, the cheese consumption in the US was 29.8 pounds. That means that on average, each person in the US consumed almost 30 pounds of cheese in that year. As you can see, cheese consumption increased during the following years. The peak was in 2007 when the cheese consumption was 33.1. In another way, Americans ate about 2/3 of a pound of cheese every week. The blue line shows the number of people who died each year from being tangled in their bedsheets. In the year 2000, 327 people in the US died from being tangled in their bedsheets. As you can see, the number of people dying in this way increased during the following year. The peak was in 2008, when 809 people died from being tangled in their bedsheets. Before going further, let's talk about what kind of people die from being tangled in their bedsheets. What kind of people die in this way? So deaths from bed sheets typically occur in elderly people who are extremely ill, disabled, demented, or heavily medicated, like people in nursing home. Why do you think the number of deaths from getting tangled in bed sheets increased during this 10 years period? One explanation is that the number of elderly people has been increasing, so there are more and more elderly people who are extremely disabled and heavily medicated living in the nursing homes. Do you think there is a relationship between the cheese consumption and deaths from tangled bed sheets? This table shows actual numbers. The first column shows each year from 2000 to 2009. The second column shows the number of deaths that year from tangled bed sheets. The third column shows cheese consumption for each year. If I asked you to, you could let the second column with the number of deaths be your X variable, and you could let the third column with cheese consumption be your Y variable, and you could calculate the correlation between the two variables. I am not going to ask you to do that today, but I have created the scatter plot showing the relationship between these two variables. In this graph, the x-axis represents the number of deaths from tangled sheets, and the y-axis represents the number of pounds of cheese consumed. Each dot represents a single year with the x-coordinate representing the number of deaths in that year, and the y-coordinate representing the cheese consumption during that year. Now looking at all of the dots in the scatter plot, is there a positive relationship or negative relationship between the cheese consumption and the number of deaths from the tangled bed? So as the number of deaths increases, what happens to the cheese consumption? Alright, so as the number of deaths increases, cheese consumption also increases. That's why we can say it is a positive relationship. So here is the line that shows the trend of the data. Is it the positive or negative z-equal line? Does that indicate the positive correlation or negative correlation? Right? So the slope of the line is positive and indicates a positive correlation. Now let's try to guess the size of the correlation. What do we look for in the graph to give us an idea if it is a small positive correlation, a medium correlation, or large correlation? So to get the idea of whether the correlation is small, medium, or large, we look at how close the dots hug to the positive z-equal line. So these dots hug pretty close to the line. So any guesses how large the correlation is? Okay, so let me calculate the correlation now. The correlation of deaths from the tango sheets with cheese consumption is 0.947. Is this considered a weak, moderate, or strong correlation? Okay, so in the previous lecture, I showed you that the correlation above 0.80 is considered very strong. So there is very strong correlation between the number of deaths and cheese consumption. Now, do you think the relationship is causal? Okay, so this is not, the correlation is huge, but it probably doesn't indicate a causal relationship. So let me show you how scientists think about it when they decide whether the relationship is causal. We will start with the definition of cause. There are actually several definitions of cause, but this definition is commonly used in psychology research and in medicine. When we say X causes Y, we mean that if we change X, then Y will also change because we have changed X. Let me show you how this definition works. Let's say we increase cheese consumption. For example, let's say we spend a lot of money on advertising for cheese and we give people rebates for eating cheese. So, if we increase cheese consumption in that way, will that also increase the number of people who die from being tangled in bed sheets? No. Even if we get people to eat 52 pounds of cheese each year, that's 1 pound of cheese per week. It's highly unlikely that the number of bed sheets deaths will shoot up. So, if increasing cheese consumption doesn't increase the number of deaths, we would say that cheese consumption doesn't cause bed sheets death. Let's try it the other way. Let's say we do something horrible that increases the number of bed sheets deaths. Will that also increase cheese consumption in the US? No, it's ridiculous to think that by increasing the number of bed sheets deaths, we will increase cheese consumption. So, according to the definition, we would say that the bed sheets death doesn't cause cheese consumption. Now, I think we all knew already that the cheese consumption doesn't cause bed sheets death, or vice versa. But this example illustrates how the scientific definition of cause works. In psychology and medicine, if we want to know if X and Y are causally related, we ask, will changing the X result in a change in Y? Or will change Y result in a change in X? In the real world, we run into some pretty important correlations, but these correlations can be controversial because there is disagreement about whether these correlations are causal or not. The definition of cause can help us to sort things out. Here's a controversial correlation. Research has consistently shows that the marijuana use is correlated with use of opiates and methylphenidate. So the controversy is this. Does the marijuana use cause the use of opiates and methylphenidate? Or is the correlation spurious? Here's how scientists would use the definition of cause to approach this controversial issue. The scientists will ask, will decreasing the marijuana use decrease the use of opiates and methylphenidate? For example, if we launched a major war on the marijuana use in the US and decreased the use of marijuana by 50%, would that also decrease use of opiates and methylphenidate? If decreasing marijuana use leads to decrease the use of these other drugs, we can conclude that the smoking marijuana causes the use of these other drugs. If decreasing marijuana use doesn't change the use of these other drugs, we can conclude that the correlation of marijuana use with these other drugs is spurious. Here's another controversial correlation. Researchers have examined gun ownership in many different countries. They have found that there is a correlation between the number of guns owned per capita in a country and the number of deaths from the mass shootings in that country. The question is this correlation causal or is it spurious? That is, does the number of guns cause an increase in mass shootings? This question can be framed using the scientific definition of cause. The question can be framed this way: will decreasing gun ownership decrease mass shootings? For example, if we somehow reduce gun ownership by 25%, will the number of mass shootings go down? Again, there is controversy about the answer to this question. Some people say that decreasing gun ownership by 25% will not affect the number of mass shootings because certain violent people will still get the guns and carry out mass shootings anyway. Other people say the opposite. It is hard to know for certain which side is right. These examples show the difference between correlation and causation. The two are not the same. Even when we know that two things are correlated, we need more information before we can conclude that they are causally related. It can be really hard to figure out whether the relationship between two variables is causal. The kind of study that psychologists and medical researchers use to answer causal questions is called an experiment. Not all studies are experiments. An experiment is a particular kind of study that can discover whether or not two variables have a causal relationship. Later this course, you will learn more about experiments and how they can discover whether two variables are causally related. But for today, it is enough to emphasize the main points. First, correlations do not necessarily indicate causality. Second, the tool that the researchers commonly use to decide whether two variables are causally related is the experiment.